Although 5G wireless technologies are nearing their first public deployment, millimeter wave technologies for public safety communications are far less understood and present some unique challenges. Here to tell us why and how to move forward with millimeter wave technology is Aditya Dhananjay. He's researcher at NYU Wireless and postdoctoral fellow with NYU's Tandon School of Engineering. And Aditya, welcome to the program.
Morning. Nice to be with you.
Good to have you. I want to start with really the significance behind the primary funding by NIST, that's the National Institute of Standards and Technology, that funding for millimeter wave technology by NYU was north of $2 million. Tell us about the significance of the funding first, but also the significance of your research.
Well, so when it comes to wireless research, the cellular industry is typically the primary driver. So most of the research that takes place is geared towards providing what the cellular industry wants, whether that is for an Internet of Things kind of scenario or mobile massive broadband. Those are the primary drivers. And what happens is that the public safety applications tend to get left behind in the ecosystem because they're not as lucrative as the cellular industry is. But we all know that, the public safety use cases are also incredibly important, and these use cases need to be kept in mind while these wireless systems are being designed and tested. So this particular award that we won is for wireless research with a focus on public safety, specifically to do with first responders such as firemen, in terms of what sort of communication capabilities they're going to need, and how in general wireless research can move forward, keeping these very important use cases in mind.
Now, of course, we're talking about the relationship between ultra high-speed wireless connectivity and first responders. What's a scenario that you can think of right now that you can envision where this type of connectivity would be useful?
Well, so one example would be if a fireman or a group of firemen have to go into a burning building. The kind of communication technologies that are available to first responders today are limited to either voice or very low resolution and low quality video. And the reason is that, most wireless networks most wireless first responder systems are based on the lower frequencies. And so when you are operating over lower frequencies, the amount of spectrum or bandwidth that is available is extremely limited. And Communication Theory 101 tells us that the amount of data that you can push through a communication link is directly proportional to the amount of bandwidth. So if you have a fireman entering a building or you have a bunch of robots that are entering a burning building, you want to be able to send data back to a control center so these robots can be controlled and the firemen can see what is going on inside the building. And so that is one primary use case. Another use case would be, if a fire department is tackling an outdoor brush fire or a forest fire, you have a bunch of drones that have cameras mounted on them, and then these drones are used to take images and videos of the areas that are basically on fire. And you want this video and these images to be sent back to a control center so that the appropriate planning can be done. And the amount of spectrum that is available today for public safety networks is very small and cannot support the sort of high bandwidth requirements such as video. And so that is one of the use cases for millimeter wave frequencies to be used in public safety applications.
Now, Aditya, you talked about narrowband or low band frequencies, also high band frequencies. Let's go a little more detail about that for our viewers. Why should public safety communications use frequencies really above 6 gigahertz in the millimeter wave spectrum?
Right. So the existing frequencies upon which public safety systems run are typically the frequencies below 6 gigahertz. And these bands are incredibly congested because you have 3G, 4G networks operating on them. You have digital TV. You have the unlicensed Wi-Fi bands. You have all sorts of incumbents that are operating on this very narrow slice of spectrum that is below 6 gigahertz. The reason that these frequencies are typically used is that the radio waves at these frequencies have got very good propagation characteristics. They can pass very well through buildings and walls and obstructions and foliage and so on. But the drawback is that the amount of data that you can push through on these frequencies is extremely limited. The millimeter wave frequencies, on the other hand, offer orders of magnitude greater spectrum. So in theory, you can really set up very high bandwidth communication links using these millimeter wave frequencies. But the challenge is that the propagation characteristics at these millimeter wave frequencies is not as favorable as the propagation characteristics below 6 gigahertz. And that is why there are a lot of open research challenges to do with how do you really design systems to leverage the massive amounts of bandwidth while still maintaining a reliable communication subsystem. And that is the kind of general area where our work sits in.
Now, I wanted to add, and you just talked about some of the challenges with millimeter wave technologies, but are we right now really in a nascent stage of studying the benefits of millimeter wave technology?
You know, millimeter wave frequencies have been used for many years for what are called backhaul links. So you have a point-to-point link that can be, a few hundred meters in length, and then you use these highly directional antennas, and you can set up a line of sight, very high bandwidth communication link from a point A to a point B. These technologies are well known. But the challenge comes with operating millimeter wave links in environments where you do not have line of sight communication between the transmitter and the receiver. So the challenges are that, first of all, at the millimeter wave frequencies, your free space or isotropic path losses are higher. And secondly, these millimeter wave signals get blocked very easily by things like concrete and bricks or even human beings. And so, but what saves us is that these millimeter wave frequencies, the signals get reflected quite easily of objects in the environment. Objects like glass or little metallic objects act as very good reflectors of these signals. So the challenge is, how do you design systems to maintain the communication even when blockage takes place by leveraging these reflections in the signal? And so that is where the challenges lie.
So as far as really designing, testing public safety communications equipment, what would I mean, I know you have some machines just right behind you. What would a simulation tool look like, or can you describe that? Maybe pertaining to open source channel sounding, emulation, and those types of things.
So there are multiple ways that you can design and test systems that operate over these millimeter wave frequencies. The first is to do over-the-air testing. And so our research group is one of the few research groups around the world that has got access to what are called these software-defined radio platforms that enable you to set up millimeter wave links at reasonably high bandwidths. So essentially, what a software-defined radio is that it is basic, like you can think of it as Legos for radios. So it consists of a large number of components that you can put together, you can mix and match to make them behave like a radio of your choice. And these systems are highly programmable. So one way of designing and testing systems that operate over these millimeter wave frequencies is to actually build it out and run the links over the air as we do in our lab. But one of the problems with this is that the time taken to run an experiment is extremely high. Of course, once you get it to work, you are very confident of the design, but the time taken to get to that, to an implementation is quite high. So the other method that is commonly used both in academia and the industry, as well as in our lab, is to use open source simulators. So NS3 is this very well-known open source, network emulator that is used for a wide variety of research problems. And in our research group, we have released open source extensions to NS3 that makes it suitable to run millimeter wave experiments on top of it. So again, right, if you're using NS3, you're not running over the air experiments, but you are doing the signal processing in such a way that you have high confidence that your simulations are going to match reality very closely. So those are kind of the tools that are used. So the first one is software-defined radio platforms, such as the one we have over here by National Instruments, and the other is the open source network simulation and emulation tools through NS3.
Now, one thing I know that NIST is happy about is that you're getting out of the lab at NYU's Wireless Research Center, and you're actually experimenting with some test beds out there, specifically with the Austin Fire Department's emergency deployment team. Can you tell us more about how you're involved with that type of research?
Right. So I think as engineers, when we sit in our labs, it's very easy to build systems that can impress our engineering buddies. But then, if people were to really use it in the real world, that's a whole different ball game. So one of the main challenges that we find is just to understand the end users and to understand how they are going to be using these wireless communication systems. And so that is why we are very lucky to be working with the Austin Fire Department, which is a very forward-looking fire department because they are early adopters of new technologies. So the Austin Fire Department is going to be working closely with us to help us understand what the use cases are, what the constraints are that that their first responders operate under, so that we can design systems that will actually be useful to them, as opposed to just a cool engineering project that does not have much real-world implication.
DT, you're doing some really interesting research, and again, in the real world as well. So NIST, I know NIST is really happy with the work that you guys are doing. It's great that you got the funding that you got. And TI now is happy to have you on the program. Love to follow up and circle back with you sometime soon.
Yeah, thank you so much. I really appreciate you taking the time.
You as well. Thank you.